Yeah, so I'll be giving you a little snapshot about a project that we're working on, this hydrologic modeling effort in the Columbia River Basin, and show you the results from our calibrations, and then also kind of a sneak peek at some of our future scenarios of hydrologic simulations. So we're working in the Columbia River Basin, and as everyone kind of has heard over the last couple of days, this is a domain in which a big pattern is basically most of the precipitation falls in the fall and winter as snow, and then historically, and then it runs off in the spring as snow melt. And so here's kind of one way of looking at the hydrology of the Columbia River Basin. So this is your naturalized flow, essentially, of the Columbia River at the Dalles. And it's kind of taken out the effects of the human effects on the basin. And so this is kind of how the Columbia River Basin responds to its climate. And so you can see kind of in the October through February, the flow is kind of low and flat, and then you see all of the snow melt peak come off. And just like all of the snow melts off and flows into your rivers and comes off. And so just remember this general picture, because we're going to be revisiting this picture throughout the talk. Because the question becomes, okay, well, with climate change, how is that general seasonality going to change? And so climate change studies are by no means new in the Columbia River Basin. In particular, there was a study put out in 2010 by Hamlet et al. It goes by a number of different names: the 2860 Project, the Climate Impacts Group Project, RMJOC1, depending on where you're coming from. But now with the advent of the suite of GCM runs from CMIT 5, one of our goals was to be able to update and enhance that existing streamflow data set. But then also what we wanted to do was get at the uncertainty that's inherent in any hydrologic projections. So we know that any of these methodological choices that you make along the way, so your choice of hydrologic model, your global climate model, your downscaling method, all of these choices will have an impact on your ultimate projections. And so we wanted to get at this question of, okay, well, what is that uncertainty? What's the spread looking like? And so what we'll be doing then is running from the period 1950 through 2100 and running a lot of different permutations of these methodological choices. We'll be looking at 10 different global climate models from 2 representative concentration pathways, and that output will be downscaled from the coarse GCM scale to the scale of the hydrologic model, which is 1/16th degree, about 5 kilometers on a side, using 3 different downscaling methods, and then running that through 2 different hydrologic models. So you end up starting to see that we end up having a lot of different permutations of scenarios. And so the 2 models we'll be running: variable infiltration capacity model, the VIC model, and the precipitation runoff modeling system, PRMS. And so the first part of this talk is about the calibration of those models. And in general calibration, the idea is that we're comparing your hydrologic simulation to an observed quantity. In this case, we're calibrating to streamflow. And the idea behind calibration is you take these model parameters that are inside your hydrologic model, and you change them, and you look at the resulting simulated streamflow, and you compare it to your observed or your reference data set, and you try and keep changing those parameters to reduce your error. With the idea being that if you can better simulate the past, you'll be able to produce with higher fidelity, project the future. And we're using, as I said, this reference data set of the no regulation, no irrigation flow time series that you saw in that earlier plot of the Columbia River flow at the Dalles. And this is flow at 180 discrete locations throughout the basin. And this was provided in by the River Management Joint Operating Committee. And so the way we're doing it is we're taking flow at each of these discrete locations, and there's actually more information than just purely the flow at that outlet. Because from the routing model, which is the model that takes stream flow at each of these individual pixels, grid cells on which we run our hydrologic model, we know how long it takes for stream flow to get from that source grid cell to the outlet. And so combining that travel time with the flow actually at the outlet, we're able to back out essentially how much flow originated in each one of these source grid cells. And so in this deconvolution, all of a sudden we're provided a distributed reference data set. All of a sudden, at every one of these pixels that you see here on the right, we have a time series for our calibration period, water years 1992 through 2001, which is very useful. All of a sudden here, this is the just 3 sample days in our calibration period for the area upstream of the Dalles. We have it also for the Willamette. This is just showing upstream of the Dalles. And this is a game changer in some sense in terms of calibration, because all of a sudden we're able to calibrate our hydrologic model on the exact same resolution on which we're running the hydrologic model. So we're able to reduce the model error at the level of the implementation at 1/16th degree. But still, the question remained, okay, so we're able to reduce model error at each one of these individual grid cells. But does that improvement in performance, is that conserved when we finally route it back down the channel and we actually compare our model simulation with these naturalized flows? And it did, it worked. So here, yet again, this black line is the same one you saw before. This is flow. There's no regulation, no irrigation flow at the Dalles. And in green and blue, you see respectively simulated output from PRMS and VIC. And the solid lines being the calibrated flow and the dashed lines being the before calibration. So that was how we were doing before, and just kind of with default out of the box parameters. But after calibration, we saw much better improvement. Our calibration statistic, which was the weekly Kling-Gupta efficiency, goes on a scale of 1 being a perfect simulation down to negative infinity. We saw increases in that KGE for both PRMS and VIC. We saw a slight increase in bias for VIC, but I should note that the streamflow time series you're seeing here are not bias corrected yet. So there will be a post-processing bias correction step, but these are just kind of how our calibrations turned out without any other modifications. And throughout the basin, it's a similar story. So this is before calibration. Yet again, blue is good performance. And on the left, you see VIC, and on the right, you see PRMS. And you see that PRMS was kind of having difficulty in the snake, but then after calibration, you'll see everything got bluer. We're still struggling in certain areas, the Deschutes in particular, but it seems like that's kind of an area that a lot of people struggle in. So, and also a lot of the red areas you see here, we have difficulty around kind of the smaller tributaries, just because the resolution of VIC and our routing model is, VIC and PRMS, it's harder to capture with greater fidelity, those smaller tributaries. So now we take these hydrologic calibrated models, and we wanted to kind of get a snapshot of what these future runs using global climate model output would look like. And so to do that, we implemented the method by Vano et al., who you'll hear from Vano in the next talk. And it's kind of this, it allows for rapid assessment of climate change impacts on hydrologic variables. And so it's a 3-step method. So first, you take your global climate model output for the basin, and you look at the projected changes in precipitation and temperature between a future period and the historic period. And so in this case, I'm going to be showing you results from the period 2070 through 2099 for RCP 8.5. So this is kind of the most extreme, most longest out scenario that we're working with right now. And so you calculate those changes and you kind of put them aside. And then you take your calibrated hydrologic model and you perturb your historic forcings by just a little bit. And you see what the change in stream flow is. What's your response, your sensitivity of your hydrologic model to those changes in precipitation and temperature. And then you take that sensitivity and you bring back in those GCM changes that you calculated before, And using these assumptions of superposition and linearity, you just combine them, those two values, and you get, all of a sudden you have this, the combined effect of those changes on the hydrology of the system. And so here I'm going to show you some results for PRMS. So yet again, this is, that black line is the same black line you had seen before. So this is the historic flow at the Dalles. And blue is your historic PRMS run. So that's how we were doing, that's our calibrated model essentially. And then every one of those faint red traces you see there is a different realization of your GCM sensitivity analyses. So that's a different GCM projected change in temperature and precipitation scaled by the sensitivity of the hydrologic model. And then as a result, you have a kind of the resulting PRMS expected streamflow for the Dalles. And then the average, so and then just the dashed red line is a sample GCM just to kind of show you. It's a bunch of different GCMs. And then your solid red line is the mean of all of those. And so what we're seeing here is we're seeing an earlier spring melt. It's a little lower. And also we're seeing this increase in winter flows. Vic is a slightly different story. Earlier spring melt yet again, but it's a little higher. And you don't have that bimodal character that PRMS had. When you put them side by side, you can kind of see these differences. And yet again, this is the furthest out you go, right? 2080s, RCP 8.5. But already we're starting to see that there's differences between these models. And yes, this is just a back of the envelope calculation, right? We're not, no future simulations were actually run through our hydrologic models. But still, we're already kind of seeing that there is uncertainty among models in this simulating, in these simulations. And so that is just one piece of the uncertainty that we're looking at in this project. And so I just wanted to kind of show you the number of simulations that are going to be coming out of this project. So PRMS and VIC, that's just this part over here on the left here. We're actually going to be taking that GCM output and downscaling it in 3 different ways. And then from 2 different RCPs for each of those methods. Well, for one of the methods, it's only one, but and then each of these scenarios, we have 10 different GCMs. And then also VIC, we'll be running 3 different parameter sets just because we've seen that a hydrologic model calibrated in 3 different ways can produce very different results. And so once you kind of count up each of these little boxes that represents a different simulation, we'll have ultimately 172 different realizations of this future period. And so I just kind of want to stress that this is, we're hoping to get at the ultimate uncertainty and how much uncertainty is inherent in a hydrologic climate change study. In terms of next steps, we'll be running those hydrologic models using all of those different 172 setups for the period 1950 through 2100, and then routing that flow to 300 different sites in the Columbia River Basin and out, actually, and we'll be doing the western part of the coastal drainages as well. And then there'll be a streamflow bias correction step. And then we'll be disseminating those results for use by stakeholders and the public expected about fall 2016. So just to conclude, first I want to just stress that this calibration that we conducted by calibrating to distributed runoff fields from this inversely routed streamflow is an effective method. And then number 2, I wanted to say that that running all of these different simulations, assessing the effect of these methodological choices is going to help us better quantify the inherent uncertainty that we're working with in this highly complicated situation. And with that, I'd be happy to take any questions.
We do have time for questions, so.
What's the scale of calibration? Are you only calibrating to the Dalles, or did you have multiple gauges you calibrated to?
Yeah, so the way, the way it works is, here. So we take the blue little map on the left that has these black dots. Those are those NRNI, no regulation, no irrigation gauge points. And using this method, we back out the reference flow for every single grid cell. And so all of a sudden we kind of decompose the known stream flow at each of these component locations into distributed flow. So we end up calibrating at every one of the 19,000 grid cells. So it's a different calibration. And it's actually, I should say it's a pretty nice computational effort, just because it's, like, once we've set it up, we can kind of throw it on our cluster and let it run, do the work itself. So it's pretty nice.
Other questions?
So, what kind of error metrics you are using while comparing these fields? What kind of error metrics?
Oh, the error metrics?
Yeah.
So our calibration, the statistic that we were optimizing was the weekly Kling-Gupta efficiency, which is, it goes from 1 to negative infinity. So, and the idea being, we chose weekly also because we weren't sure about, in terms of matching events, we wanted to make sure that we weren't biasing our performance just because we may have missed by a day a certain event. And so we were doing a weekly average as our calibration period.
Anyone else? Well, let me ask you before you move off the stage. How many of you have heard of or worked with the SIG data set? The original SIG data set from 5 years ago, including us, BPA. Okay, fair number of you. The ultimate goal is to replace that data set with this, which took a lot of the lessons learned from that data set, which that was cutting edge 5 years ago, but there was a lot that was learned, you know, as that data set was developed. And what Oriana, Bart, and others are doing is to update that data set with the latest science and getting a better understanding of it, like Oriana said, between the uncertainty of climate change and the uncertainty of all the hydrologic model assumptions you have to make to get to that stream flow. Is it big? Is it small? Never really speculated, but we're never sure for sure. So, all right. Thank you very much again, Oriana.